So this is the second video that's part of module 1. And this is going to be kind of a theoretical video. We're going to talk about the foundations of hypothesis testing. Okay. Again, here's your population. Here's your sample. Okay. This is inferential statistics. So we're taking, for example, a sample mean, and we're using this to make inferences about our population. So the last stuff that we talked about taking this sample mean and making an interval metric out of it so that we would have more information about the accuracy of this and how variable the data is. So we looked at that. That's a confidence interval. Hypothesis testing also relates to, in most cases, we're going to talk about the sample mean. We will talk about some of the other things you can test, but for the most part, a lot of things are going to be focused on the sample mean. So hypothesis test is also an inferential technique. And the most simple question is, does this equal something? So we want to test whether or not our sample mean is equal to something that we would expect it from the population. Let's say that we expect the population mean to be 80. This is what we're going to call a hypothesis. And so the hypothesis test essentially is whether or not this is equal to 80 based on the data. Okay. So that's our next step in what we're going to work with. And that's the most simplest thing to explain, is that you have an underlying population where the mean is equal to something. You're going to collect data and you want to determine whether or not this is equal to what you would expect. Now, you are not going to get sample data that is going to come out to be 80 on the dot. You might get something like 73.9. And the question is this close enough to 80? And so you need to test whether or not that is equal to that. That's the gist of hypothesis testing. We're using sample data as a window and then working with the sample metric to determine if it's equal to something that we would expect from the underlying population. Okay. I wrote this to simplify things. There's a lot, if you read through the book, there is a lot of, it's gross overkill, and I find it confusing even though it's what I've done for 30 years. So I made a simplified version of what hypothesis testing is. First, you claim something. This is your hypothesis. Then you collect your data, and this is your sort of like, this is this, like you think underlying the population mean should be that. And then you collect your data, and then from the data, you compute what's called a test statistic. Now, the wording of this is a little different in SPSS in the book. So it's kind of confusing, but this is the metric that you compute from the data. It's typically called a test statistic. I think it's called a test value in some situations, but I always refer to it as a test statistic. So after you collect your data, you can compute this thing. And then you use this, you use your test statistic and what you claimed, and you determine whether or not it's what you would have expected. It's that simple. So you have a claim or hypothesis, you have a collection of data, you compute a metric from the data, and you determine statistically, not just, looking at things. You can't just look at a sample mean of itself. You actually have to compute a test statistic based on the sample mean, which incorporates variability and other things to do the formality of the statistical testing. And you determine whether or not the data supports the claim. In other words, if I claim that the mean of the population is 80 and I get, let's say, X bar is equal to, I don't know what I did last time, 73.5, are these close enough? And there's a formal method. Now, you can't just look at them and say yes or no, because in some cases it may be, in other cases it might not be. It depends on the variability in the sample size. And so you need to actually compute this test statistic, which is a metric on a probability distribution, to do that determination. And then you use this to determine whether or not your data supports your claim. So you make a claim, you collect your data, you compute a metric from the data, and then you determine whether or not the data supports the claim. That fundamentally is what a hypothesis test is. We're going to be doing a lot of these in this course. Mod 2, Mod 2, no, sorry, Mod 1, Mod 3, Mod 4, and Mod 5 are primarily hypothesis testing. So, okay. The book is actually somewhat, I don't like a lot of textbooks, no offense to this particular one. They try to convince you that there's 3 separate methods of testing. No, there's one method of testing in multiple ways to look at and interpret the test. You can interpret it strictly in terms of the test statistic. You can also, and this is the most popular thing to do, is to look at a p-value. Now, what is this all about? This goes back to like your study of the normal distribution and something like the z-scores and then 3. The area under the curve is associated with probability. So if you look at like the probability that z is greater than 3, which is minuscule, it's going to be less than 0.01. Well, it's going to be less than 0.05. I'm not sure that's less than 0.01. And so this is something you should have done in intro stats. The test statistic method is looking at the value of the score on the axes, and the p-value method is looking at the area. Okay. So it's really just the same thing, except you're either interpreting it in terms of the test statistic or the p-value. And this is how you interpret this test statistic to make your test conclusion. But they're not 3 like different ways of doing tests. It's just the same thing, and then how you're interpreting the results, whether you're interpreting it in terms of the test statistic and comparing the test statistic with what's called a critical value, or you're working with the p-value method. The p-value method is the most widely used and consistent. Why? Because different tests will have different test statistics and stuff, but the p-value method, using the p-value method and just looking at in terms of area, and typically it's area less than 5%, so typically it's p less than 0.05 is a significant result that we'll talk about more. This is consistent across tests, and the test statistics, you'll have different test statistics for different kinds of tests. There is a third method, and that's using confidence intervals, which I actually really like, but it's not a formal testing method. I actually do that in my Stats 1 class. Because it's just easier to understand hypothesis tests that way, and it doesn't confuse people. I don't think Stats 1 really can cover the methods that we're doing unless you have like an extended or honors course or something like that. So you can actually use confidence intervals instead of formal hypothesis testing. However, they're not formal hypothesis tests, so it's important that we not, I'm not going to introduce that anymore, because for this class, I don't want you to do it that way. Okay. So let's go through this again with more details. The first step is to claim something. This is your hypothesis, so I'm going to expand on that. So you can really claim anything you want. I mean, there's no real super laws regarding claiming things. I should just check something. There's no, like, I mean, a claim is a claim. I don't know why that phases out like that. That's really strange. Anyways, so you know, you could claim that the average person alive is 2,000 years old. That's allowed. It's not a great claim. Ideally, this is like an educated claim. So hypothesis, I think, formally means an educated guess. This technically should be done before you go and collect any data. So step 1 is to claim something. Now, in the book and in most books, when you claim something, it's called the null hypothesis. Okay, this is your claim. The claim is the null hypothesis. So you claim that the mean, and again, we're going to be working on means. I'm going to write this in terms of population notation. You typically write it as H null, which is the null hypothesis. And you write that the mean is equal to 10 per se. This is what we call your null hypothesis. The alternative is everything but. So the alternative is that it's not equal to. So you're really just, it sounds like different things you're writing, but the null is what you're testing against. Okay. So you're testing if the mean is equal to something. The alternative is the mutually exclusive space when it's not equal to. And when you do your hypothesis test, your data is going to support this or this. So the hypothesis test is very black and white. You're either supporting your claim, null hypothesis, or you're not supporting your claim. And so textbooks kind of make a big to-do about, they like to have students do little exercises of writing these claims out. But really, a hypothesis test is a test against whether or not the null hypothesis is supported by the data. Okay. Then there's little write-outs. You should be able to write this out. So these are from the text. A medical researcher is interested in finding whether a new medication will have any undesirable side effects. The researcher is particularly concerned with the pulse rate of the patients who take the medicine. Will the pulse rate increase, decrease, or remain unchanged? Since the researcher knows the mean pulse rate is 82, the hypothesis is this versus this. So this is the null, is that the mean pulse rate is 82. The alternative, which is sometimes written as H1 or HA, I like HA better, but, and I don't want to be too much of a rebel, is that it's not. This doesn't go and collect the data yet. So before we collect data, we're testing whether or not the data support this or doesn't support this. Okay. This is what's called a two-sided because it's not equal to. You could actually do a one-sided. I'm not a super fan of one-sided tests. They're not particularly accurate and they're not as good. So I'm going to cover these kind of briefly, but for the most part, I want you to be focused on these two-sided tests, which is testing this versus not this. Okay. That's the formal sort of, you should be able to write out a super basic hypothesis. I'm not going to make a super big deal of that. Here's some that are the like less than greater than, just to be able to write the claims out. A chemist invents an additive to increase the life of automobile batteries. Equal to 36 months, or in this case, greater than. I would actually prefer that you did not equal to 36 months. This would make it a two-sided test. Okay. Similarly, the contractor wishes to lower heating bills using a special type of insulation. If the average of the monthly heat bills is 78, hypothesis that they're less. So you're testing whether or not the data are equal to this. Okay. I'm not a super fan of these left and right tailed tests. They're just not as good as the not equal to. This is better as a two-tailed test. And the two-tailed test will always determine if there's a difference. Whereas the one-tailed test, you'll actually miss, like, in other words, if you're testing for less than, you're actually going to miss if it's significantly greater than, which is one reason I don't like them. So we're going to mainly focus on the two-tailed test. I will talk briefly about the one-tails, but I'm actually not going to, we're going to work with two-tailed test. Okay. So that's what you're claiming. So you basically, really what you should be able to do is write this. So you're going to claim that the mean is equal to something. This is your null, and the alternative is that it's not. So when you test, you're testing this being true versus this being true. And there's no overlap. It's got to be this or that. It's black or white. Okay. After we make our claim, we're going to go and collect our data. Okay. So we go and collect data, whatever it is, we calculate a sample mean, and then from the data, we calculate this thing called a test value or test statistic. I forgot exactly. Blumen and SPSS call these, like, I always call them test statistics. As far as I know, that was the formal language until I came across these books that wrote otherwise. So what does a test statistic do? Okay. A test statistic, essentially, regardless of what test you're running, and there'll be a lot of others, it determines how far away the sample is from the hypothesized claim value. In other words, we get if our hypothesis is 10 and our sample X bar is 9.7, the distance here is going to be like this minus this, okay? This is getting kind of similar to what the standard deviation kind of metric does. So the distance from our sample mean to our hypothesized mean is going to be, in this case, negative 0.3. However, we also incorporate the variability in sample size. So we're not just simply going to subtract. We also incorporate the sample size and the variability in the data when we do our test statistics. So fundamentally, the basics of what a test statistic does is your sample mean minus your null hypothesized mean and subtracting them, and what's the difference. But we don't just include this. We also want to take into account how big a sample is and what our variability is. Okay. So the test statistic metric does incorporate those factors as well as just looking at them. But fundamentally, the gist of what a test statistic does is determines how far off you are from what your guess is. Okay. Where does a test statistic come from? A test statistic comes from a probability distribution. We haven't seen one yet, but we will in a minute. So what you're doing when you do this is you're calculating generally what's a z-score. And so it's going to be like x minus mu over sigma over the square root of n. And so you have this formula, and the test statistic metric is a z-score. Okay. And then what you're going to do, and z-scores, of course, as we know and love, are associated with area under a curve. So if you get a test statistic and it has z equal 1, we're going to want to look at what's the probability that z is greater than 1, which I actually forgot what that is. Oops, woe is me. But it's not less than 0.05. So to get a test statistic where z is equal to 1 on your standard normal distribution, that would be about here. That is the test statistic way of looking at this. Typically, you look at what's called the p-value, and that's the probability of getting a test statistic more extreme than that. This is not going to be less than 0.05. So if we had a test statistic of 1, it would not be a significant test. But this is, so you have your data, going back, you have your data. From the data, you calculate the sample mean, and then the test statistic is based on that. So the test statistic always has the data sample mean in it for a means test. And then you get this value, which is it's a z-score or a t-score, depending on how you want to interpret small samples. And the very important thing is the test statistic comes from the data, and then the reference value comes from the null hypothesis mean, and you're comparing the two, and the test statistic accounts for that. And you get a test statistic value, which is a normal distribution value, and you want to look at where on the curve it is. Okay. So if we get, here's our standard normal again, here's 1.96, here's negative 1.96. These are again the z-scores of the standard normal. 95% is between here. So effectively, 5% is here, okay, in both ends. This is the alpha over 2 business. So alpha is 0.05. It's what's in the, and then it's divided in the left and or right and left areas. Okay. So the criteria for determining whether or not what we're going to include in the test is determined by this. Now these values here are not the test statistic. This is called the critical value. I kind of think of this as the guard dog. Okay, so both your test statistic and your critical value are z-scores, and you compare them, and you have two possible situations. So you have situation 1, right? Here's the standard normal again. Here's your 1.96. Right? You have two cases. Case 1 is your test statistic is in here. If your test stat is in here, your test is not going to be significant. And in that case, your null hypothesis, you're not going to conclude that there's anything wrong with it. If your test statistic is way out here, because it's either going to be in here or in the extreme regions, this is the not equal to test. If it's further out here and your test statistic is here, then you're going to have a significant result. And that's how this works. So we're using the distribution. These are what's called the critical values, but these are just standard values. I mean, the critical values are just the values that mark off 95%. Again, this is just negative 1.96. Do this in stats 1, compute this, and you get 95%. So the 1.96 is the critical value. I like to think of it as the boundary fence between what's significant and what's not. That's just a function of the distribution. The test statistic is a value that you get, your z, it's a z value, and then you use this. And basically, where is it on here? Is it in the extreme regions of being less than negative 1.96 or greater than 1.96, or is it like in the middle? And really, that's the basics of this. If it's in the middle, well, there's nothing about your null hypothesis that's inaccurate. If it's extreme, it's telling you that your data is really super far away, because remember what this is doing. What a test statistic is doing is it's measuring how far your data are from the claimed value. So the bigger the value, regardless of whether it's plus or minus, the bigger the value of the test statistic, the more likely it's out here. And the bigger the value of the test statistic, the further your data is from your hypothesized value. The further your data is from the hypothesized value, the more likely that your data are not supporting your claimed value from the hypothesis. Okay. This is sort of best illustrated when we actually do a specific test, but the overall picture of collect data, test statistic comes from the data, and then you need to do your decision making. And so this is just illustrating the relation between a test statistic, I think this is a standard normal one, and the area associated with it. So this is the test statistic in this case is negative 2.33. And what's the area to the left that's lower than this? And the answer is it's 0.0099. So basically you have a pretty slim chance of getting something this low. So in this case, you would most likely reject your null hypothesis, because if you were not going to reject your null hypothesis, you're looking for a test statistic in here. But this is beyond the negative 1.96. So you're likely looking at a significant difference between your null. And so this would mean that your data mean is far enough off from your hypothesized mean. Okay. Accounting for variability in sample size as well. Okay. So the final thing is to use this. You collect your data, you calculate the test statistic, and then you got to make your final determination. And so your determination is always either to reject or not reject the null. Okay. And you can do it in two ways. So if I have a test statistic that's a z-score, and my test stat is 3, okay, the critical value for a two-sided test is 1.96. The test stat is 3. This is the critical value. As always, the standard normal is the standard normal. The critical value is always 1.96 to mark off the extremes. So to make the decision with the test statistic, this is going back to this mumbo jumbo about this right here. So this is the test statistic in p-value method. Okay. Which again, we're going to look at specific examples, but I want to go over this sort of at large first. So if your test statistic is 3 and your critical value is 1.96, 3 is greater than 1.96, okay? So you'd end up in a situation where your test statistic is greater than your critical value and you would reject your null. And this means basically that whatever your null hypothesis is, your data doesn't support it. Rejecting the null means the data don't support the null, okay? If you had gotten a situation like maybe your test statistic is 0.5, it would be less than 1.96. And so you would fail to reject the null. Now, the statistics verbiage is intentionally vague. We don't ever prove or disprove. We don't like true or false. We use support, not support, reject, fail to reject. And that's because statistics is kind of a perpetual game. So we always use fuzzy wording intentionally. But essentially, if you compare your test statistic to your critical value, if your test stat is bigger, it means that your data do not support the null. You reject your null. Essentially, it means your null isn't accurate, but we don't like to use words like that. If your test statistic is less than the critical value, then you fail to reject the null. This effectively means that your data is not far off from your null hypothesis. So why, for all practical purposes, your data support it. Like, you're not going to get, when you go and collect data and run a test, if your null is 80, you're not going to get your sample mean to be 80 on the dot. There's always going to be some discrepancy. So this is measuring like how far we have to account for that and look at like how far the discrepancy is that way. And so there's also the p-value method. Now the p-value method honestly is actually easier because the p-value method uses the associated area. So for example, if we have a z-score of 3, we want to look at the probability that z is greater than 3. I don't know that offhand, but I do know that's going to be less than 0.05. Alpha is 0.05. So the p-value method just tells you that the associated area, if you're less than 0.05, you reject the null hypothesis. That corresponds to the standard normal and 0.05, the 95%. That means that if your p-value is less than 0.05, you are in the extreme regions, probability area-wise, and then you reject your null hypothesis. This is equivalent to this because you'd be in the extreme areas if you had a test statistic that was bigger than the critical values. Likewise, if your p-value is greater than 0.05, you're in here somewhere and you don't reject your null hypothesis. And that's the parallel of this situation. Okay. Okay. Finally, when we make a decision in a hypothesis test, there's always some chance that we're wrong. This is the decision made on the test, and then this is essentially the truth, right? Now, we don't actually know the truth because if we did, we wouldn't be doing a test. But it's possible you reject a null given that the null is true. This is called a type 1 error. Likewise, it's possible that you don't reject it when you should have rejected it, and that's called a type 2 error. Um, this kind of thing, I teach machine learning and AI kind of algorithm stuff, becomes kind of more important there. But be aware that statistical tests, there's variability in data, and it's not, these are not completely certain, like conclusive tests. There's errors, okay? So, and that's the basics of hypothesis testing. Make a claim, collect your data, compute a test statistic on the data. The test statistic has a corresponding reference distribution where it has critical values. Compare the test statistic to the critical values either directly or with a p-value, and then you make a conclusion on your hypothesis test. Thanks.